How can we do this without going into as much content as possible? First, let's deal with the notation. So, actually, let's deal with the name. What else have you heard in reference to polymers? I'm just hoping. Let's see what's out there. Okay, so deriving the name of it, poly means multiple things. And if it means multiple things, what else could you look at? Not multiple, but singular. So if we're looking at polymers, we could also look at monomers. So the monomers would be the pieces you use to build the polymer, how they come together. Does that kind of make sense? So if we're looking at the, I don't know why I drew all over that. If we're looking at our structure here, this is our polymer. So some notational stuff that we have to be aware of. These parentheses kind of come into play. Because what we're going to go through and do when we look at a polymer is that we're going to take that parentheses, we'll ignore that one, draw this out. And what we're saying is that we take what's in the parentheses and we copy and paste. Okay, so if I copied and pasted, I would have this, right? And then I could copy and paste yet again. Did I add a carbon? I don't think I added a carbon. Chlorine. And copy and paste. Kind of get the idea? Please say yes, because I don't want to draw any more of those. Thank you. Okay, so that's our polymer. When we're thinking about the monomers, our thought process is the individual unit that was used to build this structure, okay, to get this thing. So this would, in theory, go on for thousands of repeating units. Okay, so what we want to know is what are the individual pieces that went in to make this structure that went on for thousands of repeating units. Okay, so one option would be to go through and say, well, I took the structure in black and I took the structure in red and I reacted them with each other. Okay, but for them to react with each other, what has to be true about this point and this point? Which will end up being this point and this point. Probably easiest to think about those two. What has to be true about the black one and the red one in my purple section? If I want to make this bond, what has to be true about this point and this point? If I'm going to make that structure, okay, we'll think about this backwards here. I could look at this as a negative reacting with that positive. Does that make sense? So all we're trying to do is find the connectivity so that the electrons would share between them to make the bond. Does that kind of make sense? So if we're looking at this polymer, that black point and that red point, or our arrows, need to somehow come into alignment where they would react with each other to make a bond. Right? And I could now continue that logic all the way through because this red point is the same thing as that one, just on a different part of the structure. Does that kind of make sense? So what I could go through and do, this eraser is killing me, is I could go back to that bond and say that that bond would break. Where would I expect the electrons in that bond to go? Should they go to my red carbon or to my black carbon? Why should they go to the red? Everybody tracking that? Okay, so that's what that process would go through and mean. Okay, if we continue this out, remember the red point was the same as our very first black point, so we're going to erase that off. And what we'd be saying is that that first one would be negative. So what we're now looking at is a potential monomer. So far, so good? Right? So if I put that thing into solution, okay, with a whole bunch of other things just like it, it's going to build this thing out. Okay, but we've got some problems with that individual structure. The first problem is I have a negative and a positive within that molecule. The instant I formed it, it's going to immediately go through and polymerize, which means I can't pull this off the shelf. I can't go, here's my monomer off the shelf, now I'm going to mix it to make the reaction, because it's not going to happen. The instant I have this, boom, it's the polymer. So there would be no monomer. Okay? The whole point of our polymer is that we have individual monomers that are stable on their own. So what we've got to think about is how could I make that structure, still maintaining these ideas of negatives and positives, be stable on its own. Okay? That does become a lot more challenging to kind of nuance and figure out. But there's one more piece of information that will help us with this. If we go through and look at the answer choices, how many of them show a single monomer? None of them. Which means what we've identified as this reactive thing within the black box is not a single monomer. What is it? It's two monomers. Okay? So what we've now got to go through and do is look at that structure that we've established and say, what other bond would be reasonable to have formed to get to this point? Okay? And that is absolutely a very challenging question, but what we're trying to do is reason through the pieces that we've got. Once we've got those pieces, we'll double back to the big summary that says just what can you get away with memorizing. Do you think it makes sense that this bond cleaves and I would get that black carbon chilling off on its own? No, why not? We know it already had to be negative. Right? If I cleaved that bond off, where are those blue electrons going to go? Do you think they would go with the dot? Should I put the blue electrons over here? Whoops. On my dot carbon, that single methyl? Why not? Why do we think that's a bad idea? Why is it unstable? It's small. Do better than charged. When if I put those extra electrons on there, it's not just charged, it's -2. It's actually doubly charged. We picked up the negative. The black negative was already a lone pair on that structure. That was how we broke the last bond to get here. If we're going to break that blue bond and put all those electrons onto that carbon, that's now problematic. That's going to be really challenging. Okay, we're now making it a double negative charge. So that doesn't make any sense. So let's say the electrons went the other direction. Okay, if they went over there. Okay, is that a good spot to have my electrons? What would we need to stabilize it? So if the electrons went there, what charge would be there?
Negative.
That would be negatively charged. Okay, it would be closer to the positive on the other molecule, that's right. Okay, which is a really important observation, but it's not that close. Because if it was really close, what could we do? We could do resonance, but it isn't that close. So it can't do resonance. So you're right, it's closer. I like that thought. We'll come back to that. Is this a good negative charge? Okay? And we should be able to look at it and say, no, it is not a good negative charge. Like, well, it's better than where we put it the first time. It is, but what does that chlorine have on it? A lot of electrons. And if I have a lot of electrons on that chlorine, and I put the negative charge on the carbon next to it, I've put a negative charge next to effectively a negative charge. That's not a good system. What does that mean about that bond?
It doesn't break.
That's not the bond to split to make my monomer. Okay? So let's look at the next bond. Let's look here. Let's look at that red bond. Okay? I want to split that bond. So I'm going to do this. right? I'm going to have, I guess I won't color code it like that. Or red arrow here. There's my chlorine. There's the positive charge. There's my negative charge. Where do I want the electrons in that red bond to go? Should they go with the left piece or should they go with the right piece? Why should they go with the right piece? If they did that, what could I make? I could make a neutral starting molecule. And if I have a neutral starting molecule, that I can now go to the shelf and pull that off the shelf. That's a stable molecule. It's only going to react when it's put in a system to react. Phenomenal. What happened to the other piece? It lost electrons, right? Which means what's the charge on that carbon? It's positive. What did I have right next door? Which could? And what do I now have? I have another stable piece. What did I just find? 2 monomers. Now what do I got to do? Nomenclature. Okay, and we're done. We have an answer. Okay, what we just did, I would argue, was very, 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 very challenging. Okay, but nothing we talked about there runs counter to anything you've discussed this semester. You've been given the tools to do exactly that process. Recognize the patterns within it. Start chopping things apart. As you chop things apart, acknowledge what those charges would be. Chop more things apart. Shit, that didn't work. Try a different thing to chop apart and see how you can put that together to get to a neutral structure. Kind of make sense? Okay. Is this easy? Hell no, not at all. You're definitely moving into content that barely scratches the surface of the stuff that we've talked about. Okay? This is sort of, kind of, in the radical chapter. Okay? And if we think through radicals, radicals are unpaired, a single unpaired electron, which means we have no charges when we have radicals. Okay? But we'll have individual electrons doing chemical reactions. If we look at how we processed this, we did not process this through a radical system. The way we processed this was based off of what we've already talked about, looking at charges. We just moved the electrons according to the patterns that we're already used to. Okay? So you can absolutely leverage that. Okay? Content-wise, if we drill into what the content is pushing into. Okay? So we're going to try a different way to go through and tackle it. Because, by the way, that's the answer. Ta-da, there it is. Okay? The other approach to this is taking a swing from the other direction. The other direction, I would argue, is a lot more challenging, because what we're going to do is, instead of looking at the stuff that we know is true, the question, we're going to look at the answers. Chloroethane looks like. Lies. It does not. 3 carbons. Wrong. Eth means 2 carbons. So there's my 2 carbons. And then I have a Cl connected to it. Okay? What am I want to react it with? Propene. What's propene? 3 carbons and 1 double bond. Okay? If we were going to react these with each other, how might we predict they react? This should be a really hard question. If you see the alkyl chloride, how does this particular molecule react? That reacts primarily as an electrophile, okay, at best. Okay? If we're looking at a primary chloride, we need to be doing an SN2 reaction. Okay? So we can then go through and look at the other structure. What do we see? Well, we see the reactivity of a pi bond. How does a pi bond react? It reacts as a nucleophile. Oh, cool. Nucleophiles work in substitution reactions, but to run an SN2, what kind of nucleophile do I need? I need a strong nucleophile. Is that a strong nucleophile? No. What does that suggest? Doesn't work. Those pieces don't compute. They don't add up to do chemistry that we would like to do. If we even went through and pushed on that really hard and said, well, we're just going to do it anyway because, screw the world, okay? And if we go through and run that reaction, what's going to end up happening? I'll form a carbocation as I normally would. We'll get my new green bond. Chlorine's gone, okay? And then I would have my 2 carbons. That's what we'd be talking about forming. Could this reaction continue? Yeah, it still has a positive charge, so it could continue to react. Okay, what would it continue to react with? Okay, potentially the chlorine. So let's run that. If that reacts with the chlorine, cool. Can it continue to react? Okay, so could that chlorine position now again react with the pi bond? Maybe, but lean into that. Does that look like our answer? No. All we're looking at is a single site reacting and at best just adding a string of carbons. We're not actually keeping the chlorine on the structure. We're not maintaining this branching part. To create that polymer, we had to react 2 directions. The alkene works great at 2 directions because an alkene has resonance. And in that resonance, we generate 1 carbon that is negative and 1 carbon that is positive. Those are opposite charges. That can continue to react both directions. The alkyl halide generates 1 positive. There is no possibility to continue to react off the alkyl halide. The alkene is the only one that can continue to react. Why does that become a big deal? What the hell is the point of a polymer? To continue to react. So looking at an alkane is going to be very problematic. It doesn't have the chemistry to allow me to process that out. Okay? So by answering that question, that sets me up that anytime I see an ane, it's wrong. Ane, wrong. Okay? I'm now down to 2 different answers. Okay? Because C and D both give me these enes. So what do those look like? So chloropropene, we got 3 carbons. There's the double bond. Okay, and we're talking about the chlorine being here. Why do we know the chlorine's at that position and not out over here? Then it would say 3. Okay, because we're not specifying the number, we're saying the chlorine has to be connected to the carbon of our alkene. We're talking about highest priorities. Reacting with ethene. Okay, what's the other one? With the chlorine and our propene. 3 carbons with that prop. So we could again try and go through and decide how would these things chemically react. Right? Well, if we look at that first structure, where would I move those electrons? Should I move them to this carbon or should I move them to that carbon? Green arrow or blue arrow?
Let's say green arrow.
Why?
Because a negative right next to chlorine.
Chlorine right next to that negative becomes problematic. Okay, so then this would have to come through and react. What would we generate in that? Oops, that wasn't positive, right? It was negative, and then the other one would be positive. If I copied and pasted this, would this look like my monomer or my polymer? That one becomes harder to see, but I think it actually does. I think that one actually would. Okay, but you're like, but that wasn't the answer. Well, what happens with the other one? Where would my electrons go? Here or here? Green or blue? Whoops. Keep forgetting that. So we like the green. These electrons come out, react. Negative there. Chlorine here. There's my blue bond. What's the blue bond going to connect to? Which carbon? Purple or red? What's that? Why? She's using Markovnikov rules. I'm not going to like that.
Okay, well, I got you. So it's a positively charged portion.
If we look at the intermediate that would come out of that, we want the positive charge in the more substituted position. And if we evaluate that now as our repeating unit, does that mimic our polymer? It also mimics our polymer. So which of these two is the better answer? This one is a secondary anion. This one is a primary anion. Which one's better? Primary anion is better. The bottom one is a secondary cation. The top one is a primary cation. Which one's better? Which one's your answer? Kind of makes sense? Very slow, tedious process because you're working through content you haven't seen. Okay? This would be an opportunity in practice to try and navigate how could I possibly go through and answer this and look at those nitpicking details behind it and try and reason your way through. Okay? Formally, whoops, didn't want to erase that. Can I erase everything? Mostly everything? When we're talking about our polymers and radicals, so a couple things are going to come out. Okay, so number one, nothing we drew there was radical initiated, okay, or a radical polymer. If we're talking about radical polymers, these almost universally navigate through pi bonds. Okay, so if you're going to look at monomers that are doing a radical situation, you need pi bonds. You're looking at alkenes and, for that matter, non-polar pi bonds, alkenes, and alkynes. Okay, why do they need to be non-polar? They're radicals. The point of radicals is the electrons in a bond go back to the parent ion. If it was a polar bond, would I expect the blue electrons, one electron to go to the, come on, stupid eraser, it's killing me. One electron to go to the oxygen and one electron to go to the carbon? Does it make sense for that to happen? No? Why not? Oxygen's more electronegative. So if we're going to talk about these radical structures, they're going to happen with non-polar pi bonds. That has to be a part of that system. Okay? After that, what we're now doing is how do we get them to react? If we look at two non-polar pi bonds, we're going to ignore any structures on it. What's going to happen? You're going to split 1 and 1, 1 and 1. You're like, that's a shit ton of arrows. It is a shit ton of arrows. Okay? They also don't follow any of the patterns of our normal reactions, so it doesn't make a whole lot of sense to talk about them. And when we go through and generate this structure, what we're going to see is where we're moving those two electrons in between, we now have a bond formed. We would have a radical out here and a radical over here. Come on. Radicals are inherently unstable. What do they want to do? Stabilize. By doing what? Pairing with other electrons. So what happens? The reaction continues. And which direction does it continue? Both directions, wherever we get contact. So what do we note happens in the process of this reaction? We're going to get the loss of a pi bond. So these are all going to be addition reactions because they're going to result in the loss of the pi bond. Okay? The other thing that we're going to note is that what was the effect of all the other groups? Because when we look at a pi bond, there's 4 things on there. Did they change ultimately the internal mechanism systems? Did I draw them on there to begin with? No. So do they have an effect? To a first approximation, no. Okay? The only place where they're going to come in and have an effect is going to be the stability of the radical that's formed. So if I look at position, we'll call it 3A, 4A, position 3A and 4A will have an effect on that purple radical. Position 1 and 2 will have an effect on that red radical. What's going to affect those? Well, what's the chemistry of a radical most closely approximate? A cation. So what do we want to have at those individual positions? I want those positions to be as substituted as possible to stabilize those forming radicals. Okay. How does that align for us? Well, it's the final answer that we had here. If we go through and look at this, we're looking at our chlorine structure reacting with our carbon structure. And all we're doing is recognizing that our backbone is made up of the pi bond. Backbone made up of the pi bond. Those are our two answers. So what you're trying to do is split the monomer into those individual pieces. Why do you know you need to split it into two pieces? Because it says two monomers. Okay? It could be made more difficult by only showing one monomer. I would argue this question isn't a question you would see on the ACS. Okay? Why? You have to understand polymers, you have to understand radicals, you have to understand nomenclature. That's three high-value targets to go through and deal with. What could you see on the ACS? Instead of dealing with nomenclature, you've got structures. Okay? So this is useful in the practice because it calls attention to all of that extra information and how you would manipulate it. For me personally, polymers are second semester OChem. Me extra personally, polymers shouldn't actually be in OChem. Okay? There's enough going on with the individual content that we don't need to convolute it with special circumstances for what's going on, and that's ultimately what polymers are. They're a special circumstance for the individual chemistries. We don't need to be making things more challenging than they already are. Okay? That doesn't mean you can't answer them. You can. Reason through what you can and manipulate those systems. If you're saying radical polymers, you need to be looking for pi bonds. They have to be there. Okay? Within this, because I believe that's in the radical chapter when they're talking about the polymers, okay, they won't mention another polymer because the other polymer that shows up in second semester as far as chemistry, and we end up talking a whole lot more about polymers at the tail end of second semester. Okay, polymers tend to be fun. We have a goofy lab that or I call it goofy, a goofy lab that we go through and do that's based off of polymer chemistry to actually get you exposed to some of the neatness that can happen behind it. But again, if you are interested in polymers, you're a material scientist, you're a chemical engineer, you're not a synthetic chemist. Okay? You're not going into medicine. Okay? Polymers themselves are a whole nother field of chemistry. So, if you see something and you're like, oh my God, this is incredible, how can I possibly do this? First step, skip it. Okay? Second step means you can't skip it, so you come back to it.
Try splitting it into.
Break it into the pieces that you already know information about. How would you break this structure down? Look for those commonalities. Get it into a language that's useful for you to manipulate. We've spent the entire semester talking about structures. If you see names, draw some frickin' structures. Okay? Look at how those structures could possibly interact and get towards your answer. Follow the chemistry that you've already seen. Okay? Again, full disclosure, if you're already in that boat of trying to finagle the system, you're probably already going to get it wrong, which is why it needs to be one of your last questions, not your first. Make sense? And when it pops up in the study guide, do exactly what you're doing. Ask, And yeah, more than likely I'll tell you, there's a reason you haven't seen it, and it's because I don't think it's value to add to this semester. Other questions? So most of the 5-membered rings, as I'm trying to think through the reagent list behind these, I think most of them are going to come into things that you should really just memorize. Some of the 5-membered, classifying it in that 5-member ring will help with some of the chemistry, but for the most part, it's just memorization. So if we go through and look at this system, I drew out OSO4, but it's more, I don't remember the exact Lewis structure, but let's go through and call it something like this. Whoops. May actually be double bonds all the way around. And what ends up happening is your pi bond comes out, reacts with your oxygen. What's the leaving group from the oxygen?
Electrons.
I would argue it's the pi bond, it's electrons. Okay, are electrons a stable leaving group? No. Okay, this is one of the weirdest ones in my opinion that fits in what I'm calling the 5-membered ring system. But if we're saying electrons are unstable as a leaving group, this sort of fits the pattern that we need to do a simultaneous reaction back to make a 5-membered ring. That simultaneous reaction back has to come from somewhere. Where's the most likely set of electrons that can come back to bite back on the carbon structure? If we tried to do the osmium, because that's where we ejected our electrons to, don't draw this, by the way, if you're drawing it, what would we produce as a product? Something like that. What kind of structure did we make there? A 4-membered ring. Okay? That's a highly stressed environment. Can really only happen in a couple circumstances. Your boron works sort of when we talk about it through the 4-membered ring, but it's never actually forming a 4-membered ring. What it's forming is a 4-membered transition state. And that works because the boron and the hydrogen are both very small atoms, so they can coordinate simultaneously to the pi bond. Is osmium a small atom? No, it's massive. So if we were to look at the size of osmium, it's not going to coordinate in a way that's going to make a happy 4-membered ring. So the osmium doesn't make sense to actually be having the electrons come back. So where else are there electrons? The osmium accepts the electrons from the pi bond, and then we also take another oxygen next door that removes our electrons. If we now go through and run that potential reaction or that cycle through, okay, both my oxygens are going to have satisfied octets. There's our osmium. And with all its wicked stuff out here, if we really want to do with all the electrons, think technically with a lone pair on it. Okay, and we would form this 5-membered ring, drawn very goofily in between. Okay. Why does this become important? Well, this is important only because we have stereocenters. Single stereocenter in this particular case, okay, which means we should address the stereochemistry. If we're going to go through and say the osmium coordinated with the pi bond on the top, that oxygen needs to be wedged. What about the other oxygen? It's also going to have to be wedged to make that ring. Okay? That becomes important because in the next step, when all sorts of hell and weird stuff happens with a variety of different reagents, sometimes no extra reagent specified, that tends to be an artifact of the old ACS exams. But I've seen water. I think I've seen, that might be sulfite. I don't remember which one. Okay, but some other kind of reagent in there. What ends up happening is you cleave off the osmium and you leave behind your alcohols. This is going to become important for a couple reasons. One of which I should have already addressed is that process is going to maintain the alcohols in the exact same orientation. Okay? Mechanistically, how does that happen? You don't need to stress necessarily about that. Something about how the water reacts is either coordinating to the osmium and ejecting the oxygens contained to the carbon, or it's doing backside attacks at both spots. So either way, the alcohols that you get at the end are on the same side. Okay? So this pushes what I would call a syn addition. The piece that I'm missing is that back here in this structure, we should be a little bit more explicit to show one of those bonds as dashed. Because if we're going to specify one as wedged, we should be a lot more clear about the rest of the stereochemistry on that. Okay? For that OH, we didn't really need to specify stereochemistry on it. Why not? Somebody mumbled something. There's no implied hydrogens. Because if we double back, that's a carbon, 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 carbon. There's 1, 2, 3, 4. There's no implied hydrogens. Why do I not need to specify stereochemistry there? It's not chiral. Why is it not chiral? Those carbons are identical to each other, so I don't need to specify the stereochemistry there. Okay? In a better example, we would have shown that those two carbons were different so that we would see the end result. So when we're talking about these 5-membered kind of ring structures, what I would push is instead of trying to force them into the bucket of they're forming these 5-membered rings, because at some point the mechanism behind, I believe, all of them is just going to fall apart. It's just going to do weird, goofy stuff that I can't help you to better understand because they're doing strange things. So within those, what I would do is you just memorize it. Okay? So what are we memorizing? If we are saying OSO4, okay, number 1, this is an alkene, but you're going to end with the alcohols, 2 alcohols. So we could refer to that as a diol, if we're going to bring in nomenclature, and more importantly, syn or cis, depending on how you want to memorize that. Syn is the official proper conjugation of the word. Cis would be looking at the final adjective. So syn is an adverb, cis is an adjective, if you really wanted to get into the nastiness of it. Right? And then what I'm going to attempt to do is barf out all the other ones that go through some of these weird kind of systems. Ozone is on this list. Ozone goes through and does a whole bunch of extra kind of nasty stuff, because what ozone does is it stretches that double bond and inserts a carbon. So it's going to do an oxidation. You might go, well, where did all my carbons go? Remember, these are still carbons. Okay. The problem with ozone is depending on the second condition, you get different products. Okay. That second condition is what's known as either oxidative or reductive, which is very weird to say because the overall reaction is always oxidation. You're always adding oxygens, period. It's just a question of how many oxygens do you add. So if we're going to say a whole hog oxidation, great, or do we control the oxidation? Okay, so if you oxidize all the way, what you're looking at for that, so we'll call step 2 full oxidation, is you're really looking for any reagent that has oxygen present. If you see oxygen present, you're just going to oxidize. What does that mean? You're still going to get your double bond oxygen, but if those 2 spots, R1, R2, if R1 and R2 are hydrogen, turn it into oxygen. Okay? So if we started with this where the R1 and R2 were hydrogens, what's our final answer? And this becomes fun. We could put 2 oxygens on it. Those oxygens wouldn't have complete octets, right? So what might you do? I say, oh, we can put on some hydrogens. What did you just make? Those people in lab should have a little bit of a preview on this. What you just made was carbonic acid. And what does carbonic acid do? For those people drinking sodas, decomposes into carbon dioxide. Okay? So if both R1 and R2 are hydrogens, you release CO2. Okay? I have seen a question in somewhere where they were like, what's the product of this chemical reaction? And they gave a whole bunch of weird, goofy structures, and one of the answers was CO2. And I was, CO2 isn't right. That was the answer they were looking for. All the other structures actually had something wrong with the carbon counts. Okay? So R1 or R2 or hydrogen make it into oxygen. In the case where they're both hydrogen, you turn them both into oxygens. That structure goes through another chemical reaction to make CO2. Okay? If you're looking at not full oxidation, no oxygen should be present. The standard reagent that's thrown in there is what's known as DMS, or dimethyl sulfide. Okay? And what'll end up happening is you don't touch them. Okay? So no further oxidation. Okay? If those hydrogens, if R1 or R2 are hydrogens, they stay hydrogens. Okay? How do you prevent the full oxidation? DMS scavenges extra oxygens to make DMS. Oh, it's grabbing the other oxygen, so it's changing its structure across to DMSO. Right? And if you want to know, the formula for DMS is dimethyl sulfide. So draw dimethyl ether, except get rid of the oxygen and make it a sulfur. That's DMS. DMSO, you just make a double bond between oxygen and sulfur. Right? So these are ones that I would memorize. Permanganate becomes a challenging one. Permanganate, when it's cold and typically dilute, again, takes an alkene, but it'll take it to your diol. And that diol is, again, a syn or cis diol, depending on how you want to define it. Why? Again, your 5-membered rings. Bad leaving groups within those systems. Right? That one becomes tricky because permanganate can also be in hot and concentrated. And if it's hot and concentrated, it continues to react. So it continues to react similar to what ozone goes through and does full oxidation. The other multi-ring atoms are typically going back to Diels-Alder reactions, and you're not responsible for those this semester. It's really just those 4 I can think of off the top of my head. And those 4, I would argue, are very challenging to fit into the bucket of how they match the other chemistries. That's the best that I could see. Short of just saying memorize, which I'm also saying, right? Just memorize those. Other questions? Nothing at all.
What happens to one of the carbons on the product of the ozone?
You're right. I officially didn't show that other product, so it's officially this times 2. So yeah, and so the description that I would typically do with the ozone is stretch wherever your double bond is. So it'll probably be in a much larger structure. So we could look at something like, to be extra obnoxious and do something like this. Okay? And if you're going to do this with ozone or the concentrated permanganate, what you want to do is stretch your double bond. So stretchy stretch. Stretch. And then erase the middle out of it. Put in an oxygen on both sides. Erase the middle out of it, put in an oxygen. That's your cheat. Okay?
Are they bonded or no?
The oxygens are not bonded to each other because that would exceed their typical bonding patterns. Okay? So what makes this method nice allows you to draw this product out, but then you have to consider how would you see it on a test. You're not going to see it all rolled up on itself like this because that's still technically one structure. You would see it unfolded into the lowest energy configuration, and that's where things become tricky. That's where what I would do is start first with 1, 2, 3, 4, 5, 6, just count my carbons through my answers first to be like, can I just eliminate answer choices that have the wrong amount of carbons? And then say, oh, there's only one answer left that has 6, I'm done, and move on? Or am I actually going to have to unfold that structure to see what it actually looks like? Does that make sense? The next part that you would have to address on this is going back and looking at those positions, because right here, those are hydrogens. Well, are you under oxidative conditions or are you under the less oxidative conditions? Because if you're full oxidative, you kill those, that becomes CO2. Okay? If we look at that top one, I still have a hydrogen up there, so I could go through and look at that one. I don't touch that next position because that next position isn't hydrogen. I'm only manipulating hydrogens. Okay? And then down here, officially, I have a hydrogen. And again, I don't touch that position because that's going to a carbon. So how would what be CO2? So if this is under oxidative conditions, we replace both of those hydrogens with oxygens. Okay, those oxygens are officially negative, right? And what's going to ultimately happen is the electron comes in, kicks that out, and you'd be like, oh, I can't kick that out. Multiple protonation states. You would protonate it twice. And then you end up with bent to emphasize that you have that carbon in there, and you'd get water. That's where your CO2 is coming from. Does that help?
So you get OH in the reaction?
You would get water produced also in that reaction, yeah.
As a reactant though, or OH?
As a reactant, you see some form of oxygen. So when we're talking about that full oxidation system, you're looking at some form of oxygen is present. As long as you see oxygen present, it'll eventually make the the carbonate ion. The carbonate ion, through the process of your chemical reaction, is going to turn into CO2. The details of how it turns into CO2 is ultimately something that's never really discussed. I would bet it's actually coming through the chemical workup. So if you remember all of our experiments, we ran an experiment, then what did we do? We had to clean it up. To clean it up to get our product out. In the process of cleaning it up, what are you going to add? Acids or bases. And if you add acid to the carbonate, you're going to turn it into carbonic acid, which will then turn into CO2 and bubble out of the solution. So we typically ignore the fact that there's a workup added to every single one of these reactions, and we're looking at the very final thing that happens at the very, very, very end, which is annoying, but
Well, when you're doing synthesis, should you write?
you should be aware of that. Yep. So if you did this top reaction, you were under oxidative conditions, you wouldn't show the formaldehyde, you wouldn't show the carbonate, you would show CO2 as a final answer.
So you write O3 with a base?
O3 with something with oxygen present. There's a variety of different reagents that you can throw in there. So that's why I'm saying it just has to have oxygen. So sodium hydroxide, sure. Water, yes. Hydrogen peroxide, yes. Okay, there's a whole bunch of different reagents that you could list in there. And so what I'm trying to do is avoid the scenario where you memorize one of those reagents. There's 5 or 6 different ones you can put in there. And if your focus is on the reagent itself, not on what it contains, you'll miss the question. What next? So, predict the product from the reaction shown. So what do you see? Hopefully what we see right away is the strong acid. Okay, and saying strong acid is fine, but I would argue that the next or the best approach wasn't strong acid, but is H+. That's what I see. Okay? And if you want to go, to see H+, I also see Cl-, that's okay. But when you say strong acid, you're saying H+. That's what you're saying. That should be identified right out of the gate. Because as soon as you see that H+, what do you need to find? Easier than that. I need electrons, period. So now I can go to the other structure and say, where do I have electrons? Okay? And that's where we heard a couple things. Right? Number one, I heard someone jump out right away and say the pi bond, okay, or the double bond. I would argue pi bond, again, makes more sense to go through in reference. Okay? So the rest of the structure, what do we see? A bunch of carbons and hydrogens. Are those bonds particularly reactive? No, why not?
Non-polar.
They're non-polar covalent bonds. So if I'm looking at a system where I see non-polar covalent bonds and they're doing a chemical reaction, what might I need to do to force them to react? I might need to do something a little bit radical.
Elimination.
No, radical.
Radicals.
To get a carbon-hydrogen non-polar a non-polar
Oh,
covalent bond to react, you have to do radicals. That's it.
okay.
Right? So if you're looking at a structure where all you see are non-polar covalent bonds that are carbons and hydrogens, that is a radical reaction. Okay? Officially, you have lectures on that. Again, I would push to just kind of memorize those. Okay? And in memorizing those, you're telling me all this stuff, extra stuff to memorize. It's not that much when it comes to radicals. I think it's 3 reagents. That's it. Okay? 3 reagents and 3 like how you would structure the mechanistic steps. That's it. Okay? So in this case, we've got that pi bond. We don't have to think radicals because we saw the strong acid. The strong acid is already generating charges, so this isn't radical right away. I should be focused on the strong acid. I need to stabilize those, or stabilize my positive with electrons. I can now go through and have this chemical reaction run. Depending on how I'd want to format it, it's making me really cringe to do this. But I would probably try as best as I could to maintain the overall structure behind how they were formatting it to make sure I didn't goof anything. Mostly also because all of my answer choices are formatted in that fashion as well. Okay? I think ACS is getting better about that, and they're shifting to line structures. Right? So if we now look at that, I need to add that hydrogen. Where should the hydrogen go? And we have 2 carbons that we could pick from. We'd want to put the hydrogen on the CH2 because that's where my negative is going to be. Okay? If we're thinking resonance with my electrons, it makes more sense to put the negative at the primary position versus at the secondary position. Or we could think about the other piece. I would be forming a carbocation. That carbocation should form internally, not externally. Make sense?
Where's
So-
that hydrogen go on the left of the?
I see you saying it now. Which is going to be a really important hydrogen. That's the one you're talking about? Okay. So now what happens? What's the most reactive thing you see? You see a carbocation. What might you do? Okay. So that's cool. We're gonna rein back a little bit on that. Okay. When we talk about substitution reactions, we went through and I said when we say SN1, you're supposed to say carbocation. Okay. And then the next part of that discussion was when you see a carbocation, what should you think? Rearrangement or resonance. Okay? If we go through and look at the answer choices here, that rearrangement or resonance possibility is absolutely valid, but if we go through and look at our answer choices, you will see right away answer choice B is showing no rearrangement. What they're trying to leverage is, do you just memorize that HCl adds across the pi bond? Okay? That's all they're targeting, because students will go through and memorize that fact, not the how the reaction works. Okay? Because you have the how backing up your facts, you should hopefully see the formation of the carbocation and now go, dang, can I do a rearrangement? Okay? To do a rearrangement, first I would have to classify how many carbons are connected to my carbocation, which is 2. When we talk about carbocations, if you're seeing a secondary carbocation, rearrangement should be at the very top of your freaking list, because secondary is the bottom of stability for our carbocations. Okay, so we'd want to look to say, where could we rearrange from? That rearrange from is anywhere nearby, and this is where Lorraine did a really good job of calling attention to that missing hydrogen. Okay, because what could we do? We could do that hydride shift, CH3, CH2, We have a CH2, a CH3 out there now. CH2, CH3. That now places my carbocation here. With my carbocation located there, I now have a tertiary. The tertiary is more stable than my secondary. That is a valid rearrangement. I still have a carbocation. I should consider, do I have other options? The only thing better than a tertiary is with resonance. Okay? And not tertiary with resonance, just period with resonance. Primary with resonance is a little bit gray, but more often than not is more stable than a tertiary. Right? And that does get kind of challenging for students to go through and navigate, because you, I think, lean too much in how we talk about substitution substrates with primary, secondary, tertiary. Resonance is talking about legit electrons moving. Substitution is not electrons moving. It's just nearby. Right? So are you more wealthy when you're with your rich friends and they give you money, or just when they're near you? Okay? You get more money when they actually give it to you. And that's what's happening with resonance. Okay? So now we have that carbocation. We can't do any more stability, so now our chloride can come in and react, and we place that chloride on the structure, giving us which answer? A. So B we explained away. What's going on with C? They took that CH3 and somehow moved it. Okay? Well, it's really close. Can it just move? Okay? And this becomes one of the challenges within rearrangements, because people say, well, it can't move because it's a carbon, or it can't move because it's an oxygen. This is the tricky thing with rearrangements. What things can rearrange? Everything. Everything can rearrange. Because the thing that's rearranging isn't the thing. What's actually rearranging? What electrons? The bond. The bond electrons are what's moving. So when I'm talking about this rearrangement, I'm talking about those electrons moving. Those electrons are the exact same distance away as those electrons. As, believe it or not, those electrons. And our drawing makes it look kind of as an artifact that things are in different spaces. This is why we talk so much about shape early on, so that you're more familiar with where those things are. Okay? That CH3 up at the top, even if you could do this kind of goofy long distance thing, that is now a very long distance thing. You're not moving it just click. You're moving that through empty space. Okay? That's a big, big move. Okay? On top of which, if you did that, what happens to that carbon? The positive charge goes to that carbon, which would make it a primary carbocation. That's less stable than where you were. Okay? So what's happening with this answer choice is they're trying to take advantage of people just saying, oh, it's drawn next to it so I can move it. No, you can't. Look at the bond. The bond is what moves. And the bond is not right next to it. The bond is actually significantly further away. Okay? And by pushing that, they're now just saying, how do you navigate these things? Oh, well, if I can do that, well, then I can move this next piece. You couldn't do that first move to begin with. And so what they're relying on is trying to trick people into making those answers. Kind of make sense? You won't get tricked. Why not?
Because we just went over it right now.
Because you won't look at the answer. What you will do is actually solve to get what the answer should be and now match. That's why you won't get tricked by those. Okay? The only way you get tricked is if you aren't confident in your determination of the answer and you're now guessing. You're right. It does suck then. But yeah, arguably you should lose points. Does that make sense? So process your work out. Write that stuff down so that you can manipulate it and see what's going on. Kind of make sense? What's happening? So the C was like just horribly wrong. What happened in D? I would argue D is actually not horribly wrong. C is like way out there.
They just have to. Yeah.
In D, they did that. They did that rearrangement. That's a legitimate rearrangement, perfectly valid. But what kind of carbocation does it make? A secondary. That secondary carbocation is not more stable than where we started, so it doesn't happen. Okay? Kind of makes sense? What was that? Good. That was kind of the hope. So, which of the reagents can make this product?
Just
Look at the.
keep it the main product. Those oxygens are probably going to stay the same, right?
Okay. Cool. So if you're going through and looking at this, you see these oxygens. Okay, so those oxygens should stay through your starting material. How useful is that?
Not really.
Not really. Why not? All the answers stayed. Okay, but I like it. You're trying to look for a pattern. That's good. Actually, I really liked that. What was that? I think it was you. What did you say?
The what?
What was it?
Someone said number of carbons?
Yeah, who said number of carbons? Number of carbons. That's an awesome answer. So you could go through and look at the number of carbons. How many carbons do we see in our box to start with? So 6 plus 4 plus another 4. Yeah, 14. How many do we get in A? 12. Wrong. How many answers do we get in B? Wrong. C. D. Holy crap. Good job. And what's extra special about that? It's the Diels-Alder reaction. Are you responsible for that? No. And yet, what are you able to do? Okay. Which sounds like a stupid thing. Oh, I can count. Like, why does that help me? You just got your friggin' answer. Okay. So you can process some of this. Look for patterns that can help you think through where these things are going and try to manipulate within those individual systems. This is by far a very challenging question to go through and deal with. Right? But what you're trying to do is navigate that system as best as possible. Okay? So even when you don't know, you do know. Leverage your knowledge. You are much smarter than you give yourself credit for. Make sense? You solved that way faster than you were supposed to. I don't have to go through the mechanism. It's a pretty simple one. Well, on its face, it's pretty simple. Let's backtrack that. That was it. Notice it's forming a 5-membered intermediate. Why? What's the leaving group? Electrons. Are electrons stable? Nope. So? You're in that 5+ system. 4+ technically. Here you're actually forming a 6-membered ring. So even the Diels-Alder does kind of fit that pattern. The chemistry associated with the Diels-Alder is wicked. Here it's a pretty straightforward one, but it's way, 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 way more complex than we would ever give it credit for. Right? It is a reaction that we will start second semester with because it's a really good review. It gives you electrophilic addition because you're adding an electrophile. You're doing additions, so you get that chemistry into it. Do you have any stereocenters to be concerned about?
No. The rings? Really?
Yeah, you do have stereocenters to be concerned about. So you have to worry about stereocenters. Okay. As you add different substituents to your starting alkenes, you will also get a rotation in space that you'll have to worry about. So not only do you form stereocenters, but which way the groups move will also come into play. And so you get stereochemistry, you get regiochemistry because of how it comes into alignment. Here it's symmetric, so we don't have to worry about regiochemistry. But as soon as you make it asymmetric, you get regiochemistry showing up. You get stereochemistry showing up. What orbitals are overlapping to make this? P orbitals, which means you can bring in molecular orbital theory to discuss it. There's a lot of intricate moving pieces. Okay. But you don't have to worry about that for 3 months.